A buffer solution is that solution which is composed of a weak acid and its conjugate weak base. So we have a solution composed of a weak acid and its conjugate weak base. Take an example of hydrofluoric acid and sodium fluoride solution, where you have HF/NaF. This forms a buffer solution. You can also have acetic acid and sodium acetate, or what we call ethanoic acid, occurring together with sodium ethanoate. So this is going to be CH3COO(Na). This forms a buffer solution. You can have also a solution that is going to give you hydrogen cyanic acid and existing together with sodium cyanide. So where you have HCN and sodium cyanide, you'll find that these two will form a buffer solution. Now, what are the applications of buffer solutions? So one is that we find them in laboratories where buffer solutions are used to maintain the pH of blood, that is around 7.4, and then the pH of cellular environment. So in here you find that a weak acid exists in equilibrium with its conjugate weak base. The other application is that we find it in laboratory experiments where we use these buffers, where the buffer solutions are used to control the pH of the chemical reactions. This can be in waste treatment plants, water treatment, and even in biological waste treatment plants. We use buffer solutions to regulate the pH of the chemical reactions that will be proceeding. Then we have also industrial processes. We find that buffer solutions or buffers are used in fermentation, dyeing, and pharmaceutical manufacturing. Even in household products, e.g., the buffers are found in shampoos, in detergents, and skincare products. Let's look at the components of a buffer solution. So we said we have a weak acid and its conjugate weak base, which we are symbolizing with A-. That is one. Then another one, we can find a weak base, B, and its conjugate weak acid, that we are going to be symbolizing with BH+. An example can be ammonia solution, NH3, and ammonia chloride, NH4Cl. So how does a buffer solution work? So assuming that we have added a small amount of acid H+ to any solution where there is a buffer solution, then the negative ions that are present in the buffer solution will neutralize these hydrogen ions that are coming into that solution that form. So we are adding A-, which is now symbolizing the conjugate weak base within the solution. So this forms HA. So you realize that now if you have added the acid, okay, the base is neutralizing the acid that is existing, and that means you are going to have more of the base reacting with the acid, and then still what is going to be forming is going to be acidic, meaning that the solution pH has not changed at all. In other words, these solutions always try to make sure that the pH is maintained in a given scale. So you'll find that there is almost no change in the pH. That is the functioning of a buffer solution. Now, when a smaller base is added, when you add a smaller base, for example, hydroxide ions, now the conjugate weak acid part of the buffer solution will neutralize the hydroxide ions. So we are going to be adding HA, and this is going to be forming A-, and water. So you realize that now you added the hydroxide ion and you expected the pH to rise. Now, part of the hydrogen ions, of course, from the conjugate weak acid will react or will attack the hydroxide ions and you will form more of a base. So when you form more of a base, you'll find that actually, and of course plus water, you'll find you are not going to have anything like any change in the pH because the hydroxide ions that came in were attacked by part of the acid, okay, and then you form. So when a small base hydroxide ions are added, then the conjugate weak acid will neutralize the base or the basic ions. So to form a solution with no change in the pH. So you'll find that the OH ions are attacked by the conjugate weak acid to form water and the A ions, of which the A ions, we said that is the conjugate weak base. So you'll find that at the end of the day, the solution's pH is not going to change. It's going to remain within the required limits. Let's talk about the Henderson-Hasselbalch equation. Is an equation that is going to be used in calculating the pH of a solution. Okay, that is the pH of a buffer solution, and therefore the pH of that solution is equal to pKa plus the logarithm of the concentration of the weak base divided by the concentration of the weak acid. So this is the conjugate weak base and this is the weak acid. Given any problem, you will be required to determine the concentration of the conjugate weak base and then the concentration of the acid, the weak acid. Then you already know pKa, which is the same as negative logarithm of Ka. And then it is from there, you substitute in here and get your pH. Ka is the acid dissociation constant. So this is for a buffer solution that has been made from a weak acid and its conjugate weak base. Now, if we're talking about a buffer solution made from a weak base and its conjugate weak acid, then pH, so meaning we modify the Henderson-Hasselbalch equation, this is going to be pKa plus logarithm of concentration of the weak base divided by the concentration of the conjugate acid. Let's take an example. You have acetic acid and sodium acetate. This is a buffer solution. You have a weak acid and its conjugate weak base of acetic acid is equal to 4.76. So let's look at the fact that if the concentration of ethanoic acid is equal to the concentration of ethanoate ions, then the pH is equal to 4.76 plus the logarithm. Then we have the concentration of the weak, that is the concentration of the conjugate weak base, that is ethanoate ions, and then divided by the weak acid, ethanoic acid. This is equal to 4.76 plus logarithm of 1 base 10. You will find that the pH is equal to 4.76 plus 0, which is 4.76. So in that regard, you realize that if you have acetic acid and you have also sodium acetate, which is forming a buffer solution, the acetic acid is the weak acid, sodium acetate is the conjugate weak base. So these concentrations, if they are in the same way, you'll find that when you take this calculation, it still gives you a pH of the solution that is a constant. So buffer solutions have constant pHs. Even when you add anything onto them, you'll find that there is going to be a struggle to neutralize whatever has come in to maintain a constant pH. Another example, we have ammonia and ammonium chloride. This is ammonia solution and ammonium chloride solution. So this is a buffer solution that is composed of what? This is a weak base and this is a conjugate weak acid. How do we determine the pH here? The pH we said is equal to a pKa, okay, plus logarithm. Then we are going to have the weak base NH3 divided by the concentration of the conjugate weak acid. So if pKa of ammonium ions is equal to 9.25 and if the concentration of ammonia solution is equal to the concentration of ammonium ions, then you'll find that the pH of this solution will still remain 9.25 plus logarithm to base 10 of 1. So this gives you 9.25 plus 0. So the pH still remains a constant at 9.25.